Lesson 54, Relativity breaks conservation of momentum and energy. So that's what we're going to talk about in this lesson. In the next lesson we'll talk about how it can be fixed, but in this lesson we're going to focus on seeing that it is in fact broken. Lecture 41 we talked about elastic collisions, and so the example we're going to go through today will be of an elastic collision. The first equation here is just conservation of momentum, and if you were to write that out as m1 times v1 initial, I'm putting the initial and final in the superscript position. If I were to put the particle number there, you might think it's like squared or something. This is for two particle systems only, by the way. Plus mass 2, velocity 2 initial is equal to mass 1, velocity 1 final, plus mass 2, velocity 2 final. If I rearrange this, right, and move this mass 2, velocity 2 initial over to the right-hand side and the mass 1, velocity final to the left-hand side, that's how we get this equation. So I'm just collecting particle 2 terms and particle 1 terms together. It'll make it easier to work with, as you'll see. The kinetic energy term, this comes from, it's a combination of the kinetic energy, conservation of kinetic energy, which would say 1/2 mass 1 v1 initial quantity squared, right? Plus 1/2 mass 2 velocity 2 initial squared, and then equals the finals. And again, we take this equation, we combine it with conservation of momentum, we can simplify it, and we'll get this equation here, which says that the negative of the recession velocity, right, so the difference in the velocity of recession, will be equal to the difference in the initial and the final velocity. God, I got that backwards, didn't I? Should this be final? Yes, of course. This is the velocity of recession, how fast the objects move away from each other, is the negative of the velocity of approach initially. So that's what this says. That was the result that we got in lecture 41. But here we're going to talk about an elastic collision, but it's going to be relativistic. So we'll use our typical train example. We're going to have a train, and on this train we're going to do a little experiment with some balls colliding. We have V1 initial headed in the same direction that the train is moving with respect to the platform, and V2 initial will be headed in the opposite direction, both with different masses. And then the after situation, I've kind of set it up. The numbers that we're going to use, we will get this, where the first the ball number 1 will bounce back in the opposite direction that it came, and ball 2 will move forward in the direction that the train is moving. And we're going to work it out first from the train frame. Here we don't have any problem, almost. We have to keep the velocity. Remember, we usually set the speed of light equal to 1, which means that all velocities of particles should be less than 1, right? Yeah. Well, since we're not going to use anything new, just using regular old conservation of momentum and energy, we could easily get a situation where our velocity after a collision exceeds 1. Imagine if we have a very heavy ball colliding with a very light ball. The heavy ball is moving, at a 90% the speed of light. It hits the second ball. The second ball is going to go flying away at a speed faster than the speed of light. But we'll use numbers to avoid that situation. But that would be an example of where conservation of momentum, well, I don't know if you'd say conservation of momentum break. I guess it does in a sense. But eventually we'll get a framework with which to deal with situations like this from the context of relativity. Okay? But for now I'm going to keep it kind of a simple example. The algebra, however, I'm not going to be able to just derive a couple of expressions and say, look, see, it doesn't work. Instead, what we're going to do is we're going to use some numbers, and we're going to demonstrate that it doesn't work. So I'll say that mass 1, I'll let that be equal to 2, I think. I want that to be heavy. Mass 2, I'll let be equal to 1. V1 initial, and I'm going to write everything in the train frame in black, and whenever we move over to the platform frame, I'm going to switch colors to purple or red. I'll find another pen to use a different color. So the initial velocity in the train frame is going to be 1/2, so that's a positive 1/2. It's in the direction of the velocity of the train with respect to the platform. V2 initial will be equal to -1/2, so it's headed in the opposite direction. And we have no idea what V1 final and V2 final are yet. We have to calculate that. But finally, I'm going to also state that U is going to be equal to 1/2. just to keep things relatively simple. So in the train frame, the first thing we have to do is we're going to use conservation of momentum to get, we're going to try to solve for what the V1 final and V2 final are. So using the conservation of momentum, M2 is 1, so no need to put anything there. V2, well, we don't have V2 final, so we'll just write V2 final minus V2 initial, but we do have V2 initial, so we can substitute in for that. And V2 initial was minus a half, so that's going to make this plus a half. That will be equal to minus M1, which is 2, so minus 2 times V1 final, which we don't yet know, minus V2 initial, which we do know, that is 1 half. So put that in there. I want to solve for V2 final, so that's easy to do. All I have to do is just add 1 half to both sides, distribute that minus 2, and we'll get that V2 final is equal to, let's see, minus 2 V1 final, minus 2 times minus a half will be plus 1, but we're going to subtract a half from that, so that's going to give us a half. So we'll have 1 half minus 2 V1F. And we'll call this result star 1. Put a little box around it. And this came from momentum. Now we'll use kinetic energy. I could write momentum here. We'll use kinetic energy, this term here, to solve for V2F2. And then eventually we'll set them equal to each other. So we'll write V2F minus V1F equals minus, now we have some numbers to plug in, minus V2 initial. V2 initial is minus a half. So minus times a minus a half will be plus a half. And then minus times minus V1 initial will be plus V1 initial, which is a half. And so that is going to be a half plus half, that's just 1. And so, and we'll move V1F to the right here, and so we'll get V1F plus 1. And we'll call this result star 2. If we plug star 1 equals star 2, not plug, but if we set star 1 equal to star 2, these two equations, since they're both solved for V2F, then we can write that V1F plus 1 equals 1 half minus 2 V1F. Yes?
Yes.
Solve for V1F. That will give me 3 V1F equals, that's a half minus 1. So that will give me minus 1 half. Right? Divide by 3 makes that minus 1/6. V1 final equals negative 1/6. So I can write that result into our results table over here. Now that we have V1F, we can use either of these two equations to get what V2F is, right? So V2F, I'll just use star 2. V2F is equal to V1F, which is minus 1/6, plus 1, but that's really just plus, oops, not 1, 6/6, right, which is going to be equal to 5/6. So V2F equals 5/6. Remember, these velocities, we want to keep them less than 1 because if it's equal to 1, that means it's moving at the speed of light because we're letting c be equal to 1. It doesn't matter yet, but it will. So let's just review what we have here so far. Right? This is all in the train frame, okay? And in the train frame, with the initial velocities that we gave it, we let V1 initial be going in this direction with a velocity of a half. V2 initial is headed in the opposite direction with the same magnitude, right? And the train is moving along at u equals 1 half. We haven't had to use that yet because we're inside the train frame, so we don't care. We don't know that we're moving, right?
Yeah.
After they collide, because mass 1 is twice as much as mass 2, what happens afterwards is that the velocity V1 final is headed in the negative direction, so it's kind of bounced back, okay? And the second particle, mass 2, will move with velocity of 5/6 in this direction, okay? If I had made the mass a little bit bigger or the speed a little bit higher, then of course it would be different, right? But I worked at the numbers to set it up to be a situation that's manageable. And so that's why the numbers are as they are. So that's in the train frame. Now I'm going to leave it up to you guys. I'll make it a homework assignment to just confirm that you have conservation of momentum and conservation of energy. That is, you'll write conservation of energy down, you'll plug these values in and make sure that it works, okay? It's not hard to do. But now we need to move on to the platform frame. So what do we need to do to accommodate for the platform frame? Well, the main thing right now is that we have to take into account the relativistic addition of velocities, okay? So we're going to use the relativity that we know and see if we can get the right answer, or if we get something that doesn't make sense. So in the platform frame, we'll write the following. I'm not going to have enough room, by the way. I'm going to have to end up working it out over here. But V1 initial will be equal to, well, this is going to be tricky. V1 initial, black ink, right? Plus U divided by 1 plus U times V1 initial. Okay, I have it all filled in. So, kind of rethinking my use of multicolored pens here. I thought it might make it easier than putting primes on everything. You have to put primes on all these equations, and that's kind of a pain, and it can get confusing. But this V1 initial and this V1 initial, being in different colored inks, are different numbers. This V1 initial is the stuff that we calculated in the train frame. This V1 final is what we calculated in the train frame. Same thing for V2 initial and V2 final. This V1 initial, the one on the left side of all these equations, and the V2 initial, and etc., this is the velocity in the platform frame. Okay, so it's taking account of the relative motion, the speed of the train, combined with the speed of the balls that are moving inside the train. Okay, so this is just the relativistic addition stuff that we did for velocities. Not the last lesson. I guess it'd be lesson 52. Okay, so relativistic addition of velocity. That's all this is. But that's what it is. So now what we have to do, we've done all these calculations, so we're done with this. All we have to do now is basically just plug and chug our way through this, right? So we could write that V1 initial is going to be equal to, well, V1 initial in the train frame is a half, plus this U is the speed of the train, that's a half also, divided by 1 plus U, which is a half, times V1 initial, which is, again, a half. And so that's going to give me 1 over 1 plus a quarter, which is 1 over, that's going to be 5/4. This will end up being 4/5. That V1 initial is equal to 4/5. Okay? And if we do the same, and I think you guys can see how this is going, but maybe let me let you take a crack at it. V1 final, let's work that out. All we have to do, again, is plug the numbers in. So go ahead and get out your whiteboards. Use the numbers from over here, plug it in, and see if you can get an answer for me. Okay, we're back. We worked through the fraction math. It's up here if you're interested. Let's fill in the values. So for V2 initial, we got just 0. That was an easy one. V1 final, we calculated here, we got 4/11. And for V2 final, we got 16/17. Okay. So now we can use these results to check conservation of momentum, conservation of energy. So how does that work? This will be of value to you in preparing for the homework assignment, because you'll have to do this for the train frame, where you should find that conservation of momentum and conservation and energy are conserved. Here we should find that it's not. That's the whole point of the lecture. Let's look at momentum first, right? And I guess since I'm still in the platform frame, I'll stick with the purple. How's that sound? So, conservation of momentum. So we'll want to get P before equals P after. That's what it means to have momentum conserved. So let's see, what is P before equal to? Well, it's equal to M1 times V1 initial plus M2 times V2 initial. And M1 is just 2, V1 initial, remember we have to use the platform frame numbers, that's 4/5, plus M2, which is 1, which I'll just leave it off, times V2 initial. V2 initial is 0, so it's just this, so that's equal to 8/5. Okay, so what about P after? P after is going to be M1 V1 final plus M2 V2 final. Again, M1 is 2, V1 final is 4/11, plus M2 is 1, times V2 final is 16/17. This is 8/11 plus 16/17. We'll have to find the common denominator, since 11 and 17 are both prime, and we just have to multiply them. So we'll multiply 8 times 17, 36, plus we need to multiply 16 by 11, it's going to be 176. So 11 times 17 is going to be 187, and so that in the end is going to equal 312 over 187, which does not seem to be equal to 8/5. Yes?
Yeah.
You can check it with a calculator. Somebody want to punch in 8 divided by 5? What do you get? 8 divided by 5, 1.6. 312 divided by 187, 1.67. Okay? So P before is not equal to P after, therefore conservation of momentum is broken. Now let's look at conservation of energy. So for conservation of energy, we'll do 1/2 M1 V1 squared plus, well, that's going to be messy, huh? V initial squared plus 1/2 M2 V2 initial squared should equal 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. So all we have to do is plug in the numbers that we got for the platform frame. At least this term is going to be easy because this will just be plus 0 because V2 initial is 0 in the platform. Right, remember that V2 initial was moving with the same magnitude as the train was going forward, so from our perspective it's just sitting still, right? Because it's going backwards at the same speed that the train is going forward, so it just appears to stand still from our perspective. So that one's easy. The first one, 1/2 M1, that's just going to be 1 because M1 is 2 times V1 initial squared. Well, V1 initial is 4/5, so that's going to be 16/25. And that will be equal to final kinetic energies. 1/2 M1, again, is going to be just 1. V1 final squared, well, V1 final is 4/11, so that's going to be 16 over 11 squared is 121. Plus 1/2 M2, M2 is 1, so this will be a legitimate half. V2 final squared, V2 final 16/17, that's going to be times 256 over 17 squared, that's 289, right? 289. A half of 256, we can simplify that a little bit, that's just 128. Right? And now we need to find a common denominator between 11 squared and 17 squared. So 11 squared and 17 squared, it's going to be 34,969, which is 187 squared. If you can see that that's 187 squared, then your mental math is pretty good. We'll write it like this because it's easier to write that way. So that's what we'll use for our common denominator, which means we have to multiply 16 times 17 squared, 17 squared, plus, here we've got 128 times 11 squared, all divided by 187 squared. Our fraction is great. So it gives me 2,112 over 187 squared, approximately 0.58. T before, T after, this is 0.58, and T before, 0.64. So, as you can see, they're not the same, so you can write that TB is not equal to TA, which means that kinetic energy is not conserved. Oh, it was a lot, wasn't it?
Yes.
Just numbers, just fractions, you know, is what it is. But so we find that momentum is not conserved and energy is not conserved. Okay? And it appears that we've done everything right. So we have to now ask ourselves, what is conservation of energy and momentum in special relativity? And that will be the focus of the next lesson.